Hello there and welcome back. So we have been discussing two-port networks since the last couple of videos, and in this one we'll see how two-port networks can equivalently be represented. So one way is obviously to use dependent sources. We can use controlled current and voltage sources to get equivalent circuits for the two-port network. For example, let's say if we have a V1 and V2 expressed as I1 and I2, vector column pairs I'm talking about, that is the Z parameter matrix. So we can just represent the first port of the two port with let's say a resistor Z1 and a current control voltage source Z12 times I2 connected in series, and that will give us an equivalent first port. Similarly for the second port, this can be applied for the Y, G, H parameters as well, just using parallel and series connection of resistors, conductances, um and control sources. So there is a special kind of two port, that is the three terminal two port, which is kind of special. So let's talk about. So basically, a three terminal two port is different from the two ports that we discussed so far because the it has only three terminals, that is one, two, and one dash two dash are a common terminal, that is they are at the same potential, and that's how we get three terminals of port. So in the circuit, it is observed that the Y parameter matrix Y11, Y12, Y21, and Y22. Since we are talking about, okay, I should also say that we have been talking about a purely resistive two-port three-terminal network over here. So by reciprocity, Y12 will be equal to Y21, and it is observed that Y12 turns out to be negative because it should be a passive network. It should just consume the power supplied, and it can be equivalently represented as the network shown over here in this figure. That is, from we have y11 plus y12 minus y12 and y22 plus y12 connected in the pattern shown here. This is what we call a pi network, and its equivalency to the two-port network equation, I should say, is found by using the nodal analysis on the nodes that 1, 2, and the ground one over here. And I'll not go into the derivation of that right now, but this is how it can be represented. And as I said, since y12 is negative, minus y12 will be positive, which will give a positive resistance. Everything's good over here. Now, similarly, for the Z parameters, we can have a representation, that is Z11 minus Z12, Z12, and Z22 minus Z12 arranged in a fashion shown here. This is what we call a T network. And these are some characteristics of representing a three-terminal two-port resistive network. Equivalent representations. One might as well see how the resistors have been arranged because that's important. And after going through this, we see how a general two-port can be represented, because these were the representations for only a resistive network. But what if it also has the three-terminal two-port also has dependent sources? So a general representation where y12 may not be equal to y21 is given in this particular figure. That is, the for the y parameter case, we have voltage controlled current source connected in parallel to the previous network, and in case of the Z parameter, there is a voltage. So basically, this is the general representation. Uh, and after going through this, one may just recall that Y and Z parameters, when we are talking about the same circuit, they are inverse matrices. That is, Y is Z inverse. So we can find a relation between the two networks. So at this point, I should also say that the pi network is also called the delta network, and the T network is known as the star network. So let's say in the delta network, we have minus y12 is R12, y11 plus y12 is R31, and R23. So R12 is equal to minus 1 by y12, and from finding the inverse of the Z matrix, we can find the value of y12 directly from there, comparing the corresponding elements of the matrices. This turns out to be Z11, Z12 minus sorry, Z22 minus Z12 by Z12. And on the star network, I've labeled them as R1, R2, and R3. You can see what they stand for. Like R1 is Z11 minus Z12. On substituting the values, I have found a relation between R12 and the R1, R2, and R3 resistors of the star network. And on just rearranging some of the terms, I have found a relation between the star network and the delta network parameters. That is, R12 is equal to R21, R2 times R1 plus R3 times R2 plus R3 times R1 divided by R3. As you can see, this is indeed symmetric, and so goes for R13 and R32. This parameter set will be useful for converting a star network into a delta network. That is, we know R1, R2, and R3. From that, we have to figure out what R12, R13, and R13 are. That is converting from star to delta. And this is the relation converting from star to delta. This may be quite confusing, but there can be many ways to remember that. And similarly, we have a conversion from delta to star. That is again going through the same process. We have R3 turns out to be 1 by R12 upon 1 by R13 times 1 by R12. The sum of it over the three elements, again a symmetric formula. So these are the two formulas not to be confused among each other. And the second one helps us convert a delta network to a star network. And in the coming lecture, coming short video, we will see um, a new topic, that is the first order systems and how to analyze them. So see you there. Thanks for watching.